Hey guys, in this video I'm going to talk about the second fundamental theorem of calculus. The first fundamental theorem of calculus was basically our integrals plugging in our upper bound and our lower bound and then subtracting the two values. Okay, that was giving us the area under the curve. In this video, I'm going to show you what happens when you take the derivative of an integral. So first, I'm going to begin by figuring out the integral of cosine t with respect to t from pi over 2 to 2x. So the integral of cosine t is sine t because you're asking yourself, who gives me cosine t, sine t? Then from the first fundamental theorem of calculus, I'm going to plug in my upper bound and then my lower bound. Okay, and I'm going to subtract those two. Did you guys know that the sine of pi over 2 is equal to 1? So it's just a constant. Also, anything that has no variables is a constant, like pi and e and cosine of pi and so on, okay? Or e squared. These are all constants because there's no variable there. Okay, now, if I take the derivative of this, okay, so far it doesn't say take the derivative, it just says take the integral. But if I take the derivative of this with respect to x, what would happen? Well, the derivative of sine angle is cosine angle times the derivative of the angle, which is 2. The derivative of sine pi over 2, well remember, sine pi over 2 is just a constant. Sine pi over 2 is just 1. The derivative of 1 is 0. So this final answer would be this, 2 cosine 2x. There's no plus c. You took the derivative. Okay, let's try another one. The integral of cosine t is sine t. We're going to put in our upper bound, which is just 3x squared, minus our lower bound. Great, that's all that is. We integrated. We are done. But what if I added this to the beginning of it, saying take the derivative of this integral? Well, you can pause the video and try it if you want to, or you could just watch along. The derivative of sine angle is cosine angle, but times the derivative of the angle, which is 6x. The derivative of sine angle is cosine angle, but it's times the derivative of the angle. So the derivative of the integral is going to be this. So let's take a look at these two and see if there's a faster way of just coming up with the answer than doing all of this work. When you go and take the derivative of an integral, what you're basically doing is you are plugging in the bound that has the variable. Pi over 2 doesn't have a variable, so that's why I'm not plugging it in. All I do is I plug in the bound that has the variable into the t. Okay, so now we have cosine 2x. Well, what about this 2 here? How did that get there? After you plug in the bound that has the variable, you take the derivative of the bound. The derivative of 2x is 2. Let's see if it works here. Take the derivative of the integral. Well, both of these have bounds. So I'm just going to plug in 3x squared. And do you guys remember that since it's on the bottom, there should be a minus because we always do upper minus lower. So I do have my cosine 3x squared, I do have a minus, and I do have my cosine 2x. Okay, so I do have this plugged in just to this and this. But in front of it, everyone, I have a 6x, which is the derivative of this. And in front of this, I have the derivative of this. So some of you might ask, so we don't even integrate? Well, you don't have to because you're going to take the derivative. So it's just going to bring you back to whatever this is. So let's try a quick one. This is a constant, this is a variable. I don't have anything in front of it, so if I asked you to take the integral of it, you would say sine t. And then if you plugged in the pi, you're done. There's nothing to do. You plugged in the upper minus the lower. But if I added this piece of information in front of it, then what would happen? Well, what is the derivative of sine pi? Did you guys know that sine pi is just 0? It's also a constant because there's no variable there. So this person is 0. What's the derivative of sine x squared? Well, cosine x squared times the derivative of the angle, which is 2x. Bring the minus down because you can't just throw it away. So this final answer is, could we have done that a quick way? Sure. This is a constant, so we're not going to plug this in. This is a variable, so we'll plug it in. But because that variable's on the bottom, we have to compensate by putting a minus in front of it. Don't forget to take the derivative of the variable, which is 2x. So this is our final answer. Now, I'm not going to go through it the long way, but let's just do a quick one. Okay, so let's just do t squared minus 5 tan t. And I'm going to say 7, and I'm going to say 3x squared. Great. If I want you to integrate, then you would integrate. But because I'm going to put d dx in front of it, I want you to find the derivative of the integral. They're going to cancel each other out because they're the inverses of each other. So what we're going to do is only 3x squared is a variable. 7 is a number, so I'm not going to worry about the 7. I'm going to plug the 3x squared into here, and then there's another squared, okay? I'm going to plug in the 3x squared into here, okay? And then, when I'm done, I'm going to multiply the whole thing by 6x, okay? Because we have to take the derivative of the bound. And then you'll just clean it up. All right, so that's how you do the second fundamental theorem of calculus. If you wanted to do one more, I guess we can do one quickly. Let's do x squared and 5x. These are both variables. I'm just going to put t squared. You plug in the x squared, but because it's squared, all we're doing is we're plugging this into the t. Don't forget this squared is different. Minus, we're going to plug in the 5x squared. But you have to take the derivative and put it in the front. You have to take the derivative and put it in the front. And then you should be able to clean it up. So I hope this was helpful. This is the second fundamental theorem of calculus. It says when you take the derivative of an integral, then you are basically just getting back this times the derivative of the variable in the front.